Let's discuss experimental proof of Einstein's theory of special relativity. Einstein put forward his theory in 1905. However, it wasn't easy to test this theory because, as you know by now, Einstein's theory of special relativity involves things moving at very, very fast speeds. We're talking about things close to the speed of light. And we're also talking about things in different frames of reference, different viewpoints. It's not every day that we come across things that are travelling at near the speed of light. So whilst his theory was put forward in 1905 and the maths was solid, there wasn't actually any experimental proof yet. And a very nice couple of chaps in New Hampshire in the USA devised a very nice natural experiment to test special relativity in 1941. And it involved muons. Now, this is going to talk a little bit about particle physics, which is what we're going to learn about shortly. But you don't need to really understand what a muon is to understand this experiment. But let's stop and think about what would be needed to test special relativity. We need a particle that would decay. Okay, that would be really good because then we can actually put time on things. So if we know how long something takes to decay, then we have a clock. We can basically say that things have gone a certain time if we know how much has decayed. We also need to have things that travel at close to the speed of light, c, but we also need to have things that are at rest. So these are our two different reference frames. We've got something that's moving relative to us, and then we've got something that's not moving relative to us. So this is a really nice test of special relativity. These were the conditions that these gentlemen in New Hampshire put forward in 1941, and they chose muons. Now, just a really brief bit about muons. You don't really need to understand this for your external exam, but it's nice to understand what they are. So in space, there are these things called cosmic rays. Now, cosmic rays are just high energy light rays that then interact with our atmosphere. So when it hits a nucleus, any nucleus in this case in our atmosphere, it interacts with it and pions are created. Now, pions are an unstable particle. They decay, so you'd think that'd be a really nice particle to choose for this experiment. However, pions are unstable, and since it's so high in our atmosphere still, they decay into other products themselves into things called muons. And some of these muons actually make it to the surface of the Earth. Pions are so unstable that they have a very short half-life. Muons are still unstable but have a much longer half-life than pions do. And so because of that reason, that logic there, these scientists decided to study muons. Okay, so what is a muon? Well, it's got a half-life of 1.5 microseconds, which doesn't sound like very long, but we are actually talking about particles that are moving at close to the speed of light, and they're moving at this speed. So the half-life of a muon particle is 1.5 microseconds. That's 1.5 millionths of a second. And it's travelling at a speed of nearly the speed of light. So this is a percentage. It's 99.5% the speed of light. So to get that as a speed, you'd times that by c, which is times 3 times 10 to the power of 8 metres per second. Okay? So it's going to be nearly 3, it's going to be 2.9 something, okay, metres per second, times 10 to the power 8 metres per second. So there's a bit of background to the experimental proof. Now let's explain what they actually did. So they went to a place in New Hampshire called Mount Washington. Here's, forgive my picture of Mount Washington. Let's pretend it's got some snow on its peak. And at the top of this mountain, there is an observatory that can detect the number or the rate of muons that it receives every hour from space, or just naturally. And then down on the ground here, there's another observatory that is also detecting the rate of muons per hour. Okay, so I'm just going to populate this with a little bit of information first, and then I'll speak to it. Okay, what we have here is Mount Washington, and we've got two different situations. We've got classic Newtonian motion, which is fancy physics words for, speed equals distance divided by time. You know, the stuff we do on an everyday basis. Okay, so if you go 400 kilometers at 100 kilometers an hour, it'll take you 4 hours. Okay, so let's actually use this as our starting point. So Mount Washington is 2,000 meters tall. And what the scientists in 1940 found was that at the top of the mountain, they found 590 muons per hour. My apologies for the crampedness of the screen here. Basically, let me explain this. There's a lot going on. We're really just focusing on this corner of the glass at the moment, of the screen. So this orange line just here, we're talking about, this is what the scientists actually detected. So what we're talking about here is, this is called the ground frame of reference, which is the same frame of reference as the one at the top. Because the two observatories aren't moving relative to each other, they are in the same frame of reference. Okay, there's no motion relative to each other, so that is an inertial reference frame. Okay, they're in the same reference frame. So the scientists at the top of the mountain detected 590 muons per hour, and at the bottom they detected 400 per hour. Now the mountain is 200 meters tall, 2,000 meters tall. And we need to remember here that the velocity of these is moving at close to the speed of light. Okay, so what's strange about this is that if we actually consider that speed and that distance, how long does it take to go 2,000 meters at that speed? So using that, we would use the equation of speed equals distance over time to solve for the time. And as it turns out, it turns out that the time required to do that is 6.7 microseconds. Okay, so that's how long it would take to travel that long. Now, a muon decays at 1.5 microseconds. That means half of it is lost. So if we start at 590 per hour, this here is about roughly 4 half-lives. So using classic Newtonian motion and looking at how much these things decay, we should end up with about 30 per hour. 30 per hour. This is what we would get if we did classic Newtonian motion. But that's not what was observed. So something's going on here. And this is exactly why these scientists were testing for special relativity to see whether or not it actually has an effect at speeds close to the speed of light. Okay, so this is what we should get using our logic of Newtonian motion, our standard motion, everyday motion. And yet when we approach the speed of light, or when something's moving very, very fast, something else is going on, because we haven't even gone through one half-life here, because half of 590 is about 300. Okay, but we're only at 400, so we haven't even gone a half-life here. So that means that something else is going on here. Okay, so if we actually consider special relativity, which we're going to study in subsequent videos, it turns out that we get the following observations. Now it's a little bit squished here, but this is what we've just added, is this orange circle of information. So you can see here that to travel that 2,000 metres, the time taken from the rest frame of the scientists is 15 seconds, which is 10 times as much as this one. And we haven't talked about this line here, but this line here, this is the muon's frame of reference. So imagine you're a cowboy and you're strapping yourself to your horse. You and the horse are now one. So whatever speed the horse is doing, you're doing. So what's your speed relative to the horse? And the answer is 0 because you're on it. Okay, the horse isn't moving relative to you. So strap yourself in, put yourself on the muon, and let's go for a ride. The muon is travelling from the top of the atmosphere down to the ground, or sorry, to the top of the mountain down to the ground. So you'd think that it's only going 2,000 metres, but as it turns out, the theory of special relativity actually says two strange things occur. When you travel at close to the speed of light, something called length contraction occurs. And it sounds bizarre for our everyday experience, but what is actually happening is that lengths appear to be shorter. So if you're traveling at close to the speed of light, things actually look shorter in the direction of travel. We're going to talk more about that in a future video. What a bizarre concept. The other thing that's happening is you have a look over here and we've got t equals 15 seconds. So the time has actually blown out. It's actually microseconds. My apologies. And so this here is a dilating of time, and that's actually the word. Dilating means to get bigger, kind of like your eye dilates when it gets into a dark room, it gets bigger, so it can absorb more light. So time is getting bigger, and we call that time dilation. And this is where I'm going to wrap up the video. There is a lot of information here, and I just wanted to give you a bit of a background behind some experimental proof. And the muon decay experiment is a really, really strong piece of evidence and a natural phenomenon that tests special relativity. For your external exam, you would not be expected to detail all of this, okay? What you would need to do is just describe a situation that demonstrates the effects of special relativity. So in this situation, you would have to describe length contraction or time dilation, or both, but just describe it. But you would have to describe it with the aid of an equation, which at this stage we haven't actually presented any equations or maths to do with special relativity. We've just presented some data. But as it turns out, these two numbers here match quite nicely. And I just want to point this out. If it takes 15 microseconds to travel 2,000 metres, then you can actually calculate that what your speed is, and it turns out it comes out at 0.995 c. Now the weird thing is, from the muon's point of view, it's not moving. It's not moving. But guess what's moving towards it? And the answer is the ground, very rapidly before it hits it. So it does have a speed relative to the ground. And you can actually have a look at this, that if it only takes 1.5 microseconds, that's a tenth of this. Funnily enough, the distance is only a tenth as well. So whilst the time is only a tenth, the distance is a tenth, and funnily enough, its speed comes out to be exactly the same. So the strength of this is that it doesn't matter your frame of reference, whether you're on the ground looking at the muon or on the muon looking at the ground, the maths actually comes out exactly the same, which is something that classic Newtonian motion fails at, okay? Because what we find is that this is how long it would take for it to reach the ground, but if that's the case, because of the decaying effect of the muons, we wouldn't be having many left, but we still have quite a lot detected on the ground. That's a really important fact. So there's going to be more information on this on our website.